Hey everyone, and welcome. So today, we're going to take a super fast journey through the absolute foundations of modern math. We're going to see how just a couple of simple ideas can stack up to become these incredibly powerful tools that, describe our entire world, everything from physics to finance. All right, let's jump right in.
You know, it really all kicks off with this one huge question. How in the world does math give us a language to describe reality itself? Well, the answer is in its building blocks. We're about to see how they let us group things together, connect those things, and even explore the crazy worlds of the infinitely small and the infinitely large.
So, here's our game plan. We're starting with the absolute bedrock of all math, sets. Then, we'll look at how we build connections using things called relations and functions. After that, we take a giant leap into the world of calculus with the idea of limits. And finally, we'll learn how to solve some really tricky mathematical puzzles called indeterminate forms.
All right, let's start at the very beginning. Before you can add or subtract or do anything complicated at all, you just need a way to group stuff together. And that's the incredibly simple but powerful idea behind a set.
So, what even is a set? Honestly, it's just a collection of things. Think of it like a container or a box. The only rules are, 1, everything in the box has to be unique, no repeats. And 2, you need a crystal clear rule for what belongs inside. You have to be able to look at any object and say with 100% certainty, yep, that's in the set, or nope, that's out. And the cool thing is, a set can hold pretty much anything you can imagine. It could be a group of actual people, like the computer science students right here. It could be a totally abstract idea, like the set of all prime numbers. Or it can be as simple as, a few letters or a handful of numbers. The whole concept is just super flexible.
Okay, so sets really only come in two main flavors, finite and infinite. A finite set is one that you could, at least in theory, finish counting. The set xy is easy, right? It has two things in it. But an infinite set, that one just goes on forever, like the set of all even numbers. And believe it or not, this simple little distinction is absolutely crucial for basically everything else that comes next in math.
Okay, so we've got our containers, our collections of things. What's the next logical step? Well, it's to start making connections between the things in those collections. And that brings us to the idea of relations and functions.
So how do we do that? How do we mathematically describe a connection between, say, something in set A and something in set B? For instance, how would we link a set of animals to a set of foods they might eat? Math actually has a really precise way of handling this.
It's called a relation. Now, I know that formal definition on the slide looks a little scary, especially that part about the Cartesian product. That's just a super fancy way of saying, let's list out all the possible pairings between two sets. But the core idea is actually really simple. A relation is just a set of pairs. That's it. Each pair creates a link between one thing from the first set and one thing from the second. This table makes it way clearer. See, we've got a relation between animals and food. The bear is linked to honey, but look, it's also linked to meat. The rabbit is linked to carrots. This is a totally fine relation. But the key thing to notice here, and remember this, is that one input, the bear, can connect to multiple outputs.
And that observation leads us straight to a really special, much more predictable type of relation. It's called a function. And a function has one very strict rule. Every single input can have only one output, no exceptions. Our animal example? Well, that wasn't a function because the bear had two outputs. Functions are the real workhorses of mathematics because they're so reliable. You put one thing in, you know you're only getting one thing out. It's why they're used to model pretty much everything, from a rocket's flight path to your phone's battery life.
And get this, there's a fantastic visual trick for this. If you've got a graph, how can you tell in like 2 seconds if it's a function? Just use the vertical line test. Imagine dragging a perfectly straight vertical line across the graph. If that line ever, at any point, hits the curve in more than one spot at the same time, boom, it's not a function. But if it only ever touches one point at a time, no matter where you put it, then you got yourself a function. It's a dead simple but super effective test. Okay, now we are ready for a huge conceptual leap. This is one of the most powerful ideas in all of mathematics, the concept that really opens the door to calculus itself, the limit. And this is all about understanding what a function is doing as you get infinitesimally close to a specific point without ever actually landing right on it. This notation right here is the heart of the whole idea. You read it like this: the limit of the function f of x as x approaches some value a is L. And the key word there is approaches. We actually don't care what the function's value is at a.
We might not even be able to calculate it. All we care about is what value the function is getting closer and closer and closer to as we sneak up on a.
Now, a really important part of this is that you can approach your target value a from two different directions. You can sneak up on it from the left using values that are just a tiny bit smaller, or you can come at it from the right using values that are just a tiny bit larger. And for a limit to truly exist at that point a, the value you're heading towards has to be exactly the same from both sides. Both paths have got to lead to the same destination.
And look, this isn't just some abstract philosophical concept. It's a practical tool that has very clear rules. You can add limits, multiply them, apply powers to them, and it all works out in a really predictable way. These rules give us a systematic toolbox so we can actually calculate limits without having to just guess. So what happens when you try to calculate a limit and you get a totally nonsensical answer, like 0 divided by 0? Well, that brings us to our final section, how to tackle the puzzle of indeterminate forms. And these aren't mistakes. You should think of them more like clues that tell us, hey, you just need to do a little more detective work here.
So you plug your numbers in, and you get this, 0 divided by 0. What on earth does that mean? Your first gut reaction is probably error, or maybe undefined. But in the world of limits, 0 over 0 doesn't mean there's no answer. It actually means the answer is hidden. We just have to use the right algebraic trick to uncover it.
And here is the classic three-step recipe for solving that 0 over 0 puzzle. First, you factor the top and the bottom of the fraction. This almost always reveals a common term. That's the culprit, that's what's causing the zeros. Second, you cancel that troublemaker out. And finally, you can plug your value for x back into the new simplified expression. And poof, the true limit will appear.
And for another really common puzzle, when a function goes to infinity divided by infinity, there's an awesome shortcut you can use when you're dealing with polynomials. All you have to do is look at the highest power of x on the top and the bottom. If the powers are the same, the limit is just the ratio of the numbers out front. If the power on the bottom is bigger, the limit is always 0, and if the power on top is bigger, the whole thing just flies off to infinity. It's a seriously powerful trick to solve these in seconds.
And that brings us to our final thought for today. We've gone all the way from just making simple collections of stuff to learning the art of approaching infinity. This idea, the limit, is the absolute gateway to all of calculus. It's the key that lets us find the speed of an object at one single instant, or the exact area under a crazy-looking curve. So the question I want to leave you with is this. Now that we know how to get infinitely close to things, what other impossible problems are suddenly within our reach?